Hello and welcome to this video. In today's lecture, we will study the exercises 17, 18 and 19 from the chapter 3 of the book Contemporary Abstract Algebra from Joseph Gallian. Okay, the statement of question 17 is that for any group element A and X, prove that the order of A and the order of XA X inverse is same. Okay. Let the order of XA X inverse is n and order of A is equal to m. Now we have to show that we have to prove that n is equal to m. Okay. Now since XA X inverse order is equal to n, this means XA X inverse raised power n is identity. The order means is the least positive integer such that if we take the power we will get identity. Okay. This means this can be written as XA X inverse, XA X inverse, XA X inverse plus so on. Okay, no, not plus, it is product of these elements, so on XA X inverse is identity, and these are n times. Okay, if we see we can combine this as A into X inverse X, A X inverse X up to so on X inverse X A, and X inverse is equal to identity, and these terms are identity because X and X inverse are being multiplied, and we get X into A and so on into A into X inverse is equal to identity, and these A are n times, and we get that X A n X inverse is equal to E. Okay, if we multiply both sides with X inverse, pre-multiplication with X inverse and post multiplication with X, we will get X inverse into X, and we will get an is equal to identity. Okay, because the order of A is equal to m, and we get another positive integer n such that an is equal to identity. This means m will be less or equal to n because this m is the least positive such integer. Now consider, let order of A is equal to m. This means am is equal to identity, and that can be written as x times am is equal to x, and x am x inverse is equal to x inverse, and if we expand this a and that will be identity, and between every two a's we will insert x inverse and x up to so on, and these terms will be m terms, m times, and that will be xa x inverse raised power m is equal to identity. And because the order of xa x inverse is n, this means that n is less than or equal to m. If we combine these both inequalities, we will get the equality. This means m is equal to n, and that is what we want to show. So we have proved that the order of xa x inverse is equal to order of A. Now we move to the next question, which is question number 18. The statement of question number 18 is, prove that if A, this A, is the only element of order 2 in the group, then A lies in the center of the group. Means A commutes with every element of the group G. So we'll start the solution. Let A is the only element of order 2 in a group G. Now we have to show that this A belongs to the center of G. Okay, also because A has the order 2, this means A square is equal to identity element. Now we have to show that XA is equal to AX for all X belongs to G. Alright. Now let X belongs to G be arbitrary element of G. Now consider the element XA X inverse. Now consider XA X inverse whole square, and that will be XA X inverse, XA X inverse, and that will be XA, and the product of these two elements will be identity. So now this A element and then X inverse, and we know that X A square X inverse, and this A square will be identity because of given condition, and that will be X inverse, and that will be E. So we have found another element which is non-identity, that is this one has the order 2, but we know that A is the only element with order 2. So this means this element is also actually A. So XA X inverse is equal to A, and this means XA, if we move this X inverse to the right side, we will get AX for all X belongs to G because X was arbitrary, and that is what we want to show. This means A belongs to the center of G. Okay, we move to the next question. Question 19, and the statement is that prove that no group is the union of two proper subgroups. The second part is, does the statement remain true if 2 is replaced by 3? Okay, we start with the first part. Let G be a group, and we have to show that G cannot be the union of two proper subgroups, but we assume on contrary, suppose G is equal to H union K, where H and K are two proper subgroups of G. Two proper subgroups of G. Okay. Since H and K are proper subgroups, so there must exist elements. Okay, instead of here we write here, there must exist H which belongs to H but not K, and another element K which belongs to K minus H, means belongs to K but not belongs to H. Okay, these two elements, now consider these two elements also of course belongs to the group G, and if H and K belongs to G and G is a group, this means their product also belongs to G. So now there are two possibilities, either this product belongs to H or product belongs to K, because G is equal to H union K. Now if this product HK belongs to H, this means H inverse, because this H belongs to H, so its inverse will be also in H. And now the two elements HK and H inverse both belongs to K, and H is subgroup of G, so their product, which is actually equal to K, belongs to H. A contradiction, because this K belongs to K but does not belongs to H. And similarly, if this HK belongs to K and also the K inverse belongs to K, this means HK K inverse, which is actually equal to H, belongs to K. But we know that this H belongs to H but not K, so this is also a contradiction. This means HK belongs to G, but this HK does not belongs to the subgroup H, and also this HK does not belong to the subgroup K, and this means G cannot be written as union of two proper subgroups. Now we will check the statement is true for 3 or not. Okay, and we will prove that by example that the statement is not true for 3 instead of 2, means we can have a group and 3 proper subgroups, so that the group can be written as the union of those subgroups. It is easy. We considered the group of Klein 4 group. We know that this group V4 consists of 4 elements, that is identity and 3 reflections. Each have the order 2, and we have 3 subgroups H1, which is identity and A, and H2, which is identity and B, and then H3, which is identity and C. Clearly this V4 is union of H1, H2 and H3. So the statement is not true if instead of 2 we replace 3. That's all about this lecture. Thank you for watching. Please subscribe the channel and like the video.